Okay, so welcome everybody back to class. It's been a month. It's good to see all of you. Happy New Year. I hope you all had a very good Christmas and a good New Year's, and I'm excited to be back for the spring semester of this class. If you haven't looked at your WhatsApp, we just got a message from Deborah that the data should be reimbursed tomorrow. So we will keep that conversation going on WhatsApp, and everybody should expect their data reimbursements tomorrow. And if it's not happening, then please let us know. And I'm sorry that we weren't able to get the data sent out earlier today. But hopefully the problem will be all fixed today and we will figure it out to get you your reimbursements for tomorrow. So especially because we want to make sure that everybody gets reimbursed, please type your name into the chat now so that we have a full record of everybody who joined the class and who's eligible for reimbursement. Okay, so several people have written already, but especially for, I think, Scholastica, you just came into the room. Please remember to type your name so that we can make sure that everybody gets a data reimbursement who needs it. Okay, great. So I sent out a syllabus a week ago. It's not so different. I mean, we're just continuing where we left off. We're gonna continue with calculus this year, and maybe let me just quickly bring up the syllabus just so that we can go over it. Let me just go grab it. Hi, I'm doing well. How are you? Okay, let me share my screen here. This is going to work. Sorry, Tony.
No, I'm sorry. I'm
Oh,
sorry.
okay. Oh, no worries. Um, okay. So just wanted to quickly share the syllabus. I'm not going to go over everything. I mean, everything is the same. The Zoom is the same. The password is the same. The YouTube channel is the same. I just wanted to quickly show the schedule, right? So today is mostly a review class. We're going to review this optimization, maximizing and minimizing that we started with last time, and that is, one of the core applications of calculus. And I felt like last time I had to rush and go a little bit too fast at the end. So I want to do a lot more examples of that. And it will also be good to do a review class today because I'm sure some people won't make it because of the data. So I don't want to start a new topic that all of them will miss. So we'll have a review today. And then basically the next 5 weeks we have more of what would be called differential calculus. So applications of derivatives, ways to take derivatives, things like that. So these topics, which we'll talk more about, curve sketching, the chain rule, related rates, linear approximation, Newton's method, and L'Hopital's rule. So this is what we're going to do for the first month. Then we're going to have a little break on February 27th and March 6th. And then we're going to talk a little bit about what's called integral calculus. We're not going to do that much of it, but we're going to talk about kind of the reverse process for differentiation and what kinds of applications that has. It turns out that that has lots of applications. So that will be the main topic for March and April. So antiderivatives, the relation to physics and motion, relation to areas, relations to probability and statistics, and relations to physics in terms of calculating work and energy. That's going to be this unit for late March and early April. Then we'll have a day where we talk about differential equations with one particular application called exponential growth, which is very important in biology and in finance and in physics, especially radioactive or physics of radioactivity of nuclear physics, things like this. So and also in chemistry for certain types of reactions. So I'll have a day on differential equations and exponential growth. And then we're going to finish the unit with sequences and series, part of which is, I think, in the 12th grade mathematics curriculum. So we'll talk about arithmetic and geometric sequences, and we'll talk about arithmetic and geometric series. And then we'll have a final class where we talk about writing out functions as series. Turns out there's lots of functions that it can be often convenient to write them as series, and this will have various applications in physics as well. This is what's called the Taylor series or the Maclaurin series, if you've seen this. So yeah, so that's basically the plan for the spring semester. And there are a couple of days with no class. In particular, this May 8th with no class. That's going to be the week of the WITS mathematics competition that I think some of you have coached teams for in the past. So that will happen again this year. It's a high school mathematics competition based out of South Africa that Liberia has participated in for the last few years, and that will take place on the week of from May 5th to May 11th. So that week we're not going to have class because people may be busy with that and with the end of the year. Okay, so this is the syllabus for this semester, but today we're just going to review, what we know about derivatives and go a little bit slower through optimizations so we can do some more examples because it really is maybe the most important application of calculus, and so I don't want to rush it through. I want to make sure that it stays with us. Okay, so let me stop the share of the screen here. Um, Okay, let me reshare this. Oh, wait, it's working? Is it working? Okay, wow. I didn't think that was going to work. Great. Okay, it's maximized now.
Hey, I'll stop while
This is
you're
good.
doing that.
Okay, good. Oh, good. And some more people are coming in. Great. All right, so welcome Uriah, welcome James, welcome to Armstrong and William. Okay, so we have enough of a core group to do class today, and then hopefully more people next week when the data is working out. Okay, good. So let me just review what we were talking about last time with optimization and what it means and why we do it. So this we've been studying calculus, all of these things about slopes of tangent lines and taking derivatives and taking limits. And it's nice and it tells us something geometric about graphs, but really, why do we do it? What's the point? And so the main point is this question that we are not the main point, but a main point is this question that we were talking about last time, which is how do we find the maximum and minimum values of a function on some interval? And you can phrase this in the abstract, just like here we have a function f of x, and it's on some interval a to b, and we want to know what's the largest value it takes and what's the smallest value it takes. But it's not just a question about abstract math. It can be used to model lots of applications. So, for instance, what is the most economical shape to create packaging for a product in? What is the maximum acceleration on a space shuttle mission? How much of a product should be manufactured in order to minimize the average cost of manufacturing? And what is the largest area that can be fenced in by a certain amount of fence? So, all of these are types of questions that can be phrased in terms of calculus, in terms of a maximum or a minimum of a function on a certain interval. So, like we did last time, we're going to first discuss optimization problems in the abstract just with a function, and then later on we'll do some more practical applications, at least some sort of word problems that we can see, how this is going to work. Okay. So but before we actually do any problems, I just want to recall a few definitions. So suppose we have a function f and it's defined on a domain D. And for this domain D, we should really think of D as an interval. Okay, we should think of it as an interval, maybe an open interval, maybe a closed interval, maybe infinite, maybe finite. Doesn't matter. But some sort of interval is what we should think of, is how we should think of this. And so we have these four definitions. We have absolute maximum, absolute minimum, local maximum, and local minimum. Okay. And what do these things mean, right? So the definitions here again might look a little bit complicated, but the ideas are pretty simple behind them. So we'll draw pictures to show what it means. But if we have some value c in our domain, so something that we can plug into our function, then f of c is an absolute maximum of f on the domain if f of c is bigger than or equal to f of x for all x in D. This just means, yeah, right, it just means that f of c is the biggest the biggest of all f values on D, right? So it's just the biggest value that the function takes on. Okay. And similarly, we have an absolute minimum, exactly the same definition, except we say if f of c is less than or equal to f of x for all x in D. So this just means that, f of c is the smallest of all f values on D. This is what an absolute minimum means. So we talked about these last time. And then now if C is in D, then f of C is this shouldn't say n, this should say is a local maximum. A local maximum means not necessarily that it's the biggest value in the entire interval, but just that f of c is bigger than f of x whenever x is close to c. So it's kind of like imagine a little hill in the middle of a large mountain range, right? The summit of the little hill is a local maximum. It's higher than all of the points around it, even if it's not the absolute highest point in the mountain range. Okay? And similarly, a local minimum means that f of c is lower than f of x, not necessarily for every x in the domain, but at least for every x that is close to c. Okay? And then sometimes we use this generic word extremum here to mean either a maximum or a minimum. So for instance, let me just draw a picture. This is a picture that we had last time. But if I have a function that looks like this, so y equals f of x, if I have something that looks like this, let's say this is the graph of f of x, then over here, so something over here, this is a local minimum, right? Because it's lower than everything that's close to it, but it's not the absolute minimum. The absolute minimum is over here, right? Because this value of f of x is even lower. So this is the absolute minimum. And this absolute minimum is also a local minimum. And now, similar idea, this over here, it's a local maximum, right? Because the y value here, the value of the function, is larger at this particular point than at any nearby point, but it's not the absolute maximum, right? The absolute maximum takes place over here, right? This over here is, I'll just write it like that, absolute and local maximum. Okay, so we can have local minima and maxima that are not necessarily absolute minima or maxima. But if you have an absolute minimum or an absolute maximum, that's always also going to be a local minimum or a local maximum. Okay, so these are bigger than the nearby points, but they're not the biggest in the entire function. This over here is the biggest in the entire function, and this over here is the smallest in the entire function. Okay, so does this idea of local minimum, local maximum, absolute maximum, does this make sense? Or are you refamiliarized with it from last time? All right, there's no questions. I assume it's okay. So what does this all have to do with calculus? So if you
Yes,
recall,
that
yes,
August.
question, Princeton, yes.
Yeah, you just mentioned that we let's go back. Okay, the absolute maximum can also be called a local maximum minimum rather minimum.
Hmm.
So can the absolute minimum also be sorry, a local minimum also be absolute minimum?
Yeah, yes. So every absolute, if you have an absolute minimum, it's always
I'm saying
also a
I'm
local
saying
minimum.
I'm saying can a local minimum also be a absolute minimum?
It
That's my
can,
question.
but not always, right? So here we have two
Okay, okay.
different local minima. right? This is a local minimum and this is a local minimum. They're both smaller than any nearby values. But
Oh, okay,
between
okay,
these
okay,
two
okay.
local minimums, only this one is also the absolute minimum, right? This one here is just a local minimum. It's not an absolute minimum, right?
Okay.
And same thing for maximum. We have two local maxima here, but only this one on the right is an absolute maximum. The other one is just a local maximum. By the way, I
Okay,
should
thank you.
mention, maybe I'll just mention back everything here. Everything that we do today is taken from chapters 3.1 and 3.5 in the book, which I sent out last week. Okay. This is all from chapters 3.1 and 3.5. Okay. So this is graphically what local and minimum and maximum mean and what absolute minimum and maximum mean. Okay, great. So, what does this all have to do with calculus? We're talking about minimums and maximums, but our calculus, remember, is about limits and about derivatives and things like this. So, what does this all have to do with calculus? Sorry, one second. All right, so what does this all have to do with calculus? Well, remember the main concept of calculus that we talked about last semester was the derivative, right? So that if we have a function f of x that's differentiable at x equals a, then f prime of a gives the slope of the tangent line to the graph of y equals f of x at x equals a. So if I draw just another picture here, I'm not going to give you a formula, but let's just say I have a function. I'm drawing the graph of y equals f of x, and let's draw it kind of similar to what we had before. So something like this. So if this is my function, y equals f of x, then in particular, I can draw the tangent line at various places. I can draw a tangent line here. I can draw a tangent line here. I won't draw the whole line. I'm just going to draw part of the line. I can draw a tangent line up here at the local maximum, and a tangent line down here at the local minimum, which is also the global minimum. And then I could draw a tangent line over here at the maximum, and then maybe I could draw a tangent line over here. Kind of looks like this, right? So I have all of these different tangent lines that I can draw to this graph. And each point has its own tangent line. What makes a minimum absolute? Sorry, I see a question. Absolute means that it is the lowest point on the entire graph, right? So if you go back to the definition, absolute means that f of c is the absolute minimum if f of c is less than or equal to f of x for all x in the domain. So it means that every other point on your graph needs to be at least as high. So on our graph here, this one is the absolute minimum because it is the lowest point on the graph. The entire graph lies above this absolute minimum, right? The entire graph lies above it. Whereas this point over here is not going to be an absolute minimum because there's stuff on the graph that's lower than it, right? It's not the lowest the graph gets. It gets even lower down here, right? So the absolute minimum over here is the absolute one because it's lower than every other point on the graph. And here the absolute maximum is the absolute one because it's higher than every other point on the graph, right? The entire graph lies between the absolute minimum and the absolute maximum. Okay. All right. Good. Okay, so here we have all of these tangent lines. And one thing to observe is that whenever we have a local minimum or maximum, look at these tangent lines. We've got this tangent line here at the local minimum, this tangent line here at the local maximum, this tangent line here at the local minimum, which is also the absolute minimum, this tangent line here at the local maximum, which is also the absolute maximum. And if you notice something about these tangent lines, it's that they are all horizontal, right? So when the graph is going down and then up, or if it's going up and then down, or down and then up, or up and then down, at any one of these local maxima or minima, you've got a horizontal tangent line. So let me write that down. So horizontal tangent line at the local extrema. And what does a horizontal tangent line mean? Well, remember, the derivative of the function at one of these values is the slope of the tangent line. So what's the slope of a horizontal tangent line? Well, a horizontal line has slope zero, right? It's rise over run, and it has no rise. So it's zero over the run, which is zero. So this defines the relationship between the derivative of a function at a point and the slope of a tangent line at the point. Right, as James said, the relationship is that they're equal, right? F prime of A is the same thing as the slope of the tangent line to the graph at x equals A. So in particular, these local extrema have horizontal tangent lines, which means that f prime of A is equal to 0 at local extrema. Okay, so the derivative is going to be 0 when you have one of these points that's a maximum or one of these points that's a minimum. And in particular, that's as we'll see on the next slide, this is basically an if and only if, is that you can use this in reverse, and this is where calculus becomes useful, is you can use this in reverse to find the maximum and minimum values by finding all the places where the derivative is equal to 0. So the derivative being equal to 0 is going to tell you exactly when you're at a local maximum or when you're at a local minimum, right? These points in between over here, these derivatives are not equal to 0. These are some positive slope lines. These are some negative slope lines over here, but the derivative is definitely not 0. The only places where it's 0 are at the local maxima and the local minima. That's where you've got these horizontal tangent lines where the derivatives are 0. Okay. So, um, so I'm going to write this up a little bit more formally on the next page. But if you recall, this is the basic idea, which is that this is the basic idea, which is that doing algebra with the derivative, figuring out whether the derivative is 0, corresponds to being able to see something geometric about the graph. It allows you to see whether you have a point that's a local minimum or a local maximum. Okay? Because remember, horizontal is the same thing as the slope being 0. So let me write this out a little bit more formally here on the next slide. So here are the two major theorems that we're going to use, and we did this last time. I'm just going over them. It's been a month. So these are pretty intuitively clear based on the picture that I drew. If you want to really prove it carefully, that's actually not so easy to do. But we're not going to do that. We're just going to stick with the intuition. Although if you really want to read the proof of one of the theorems, you can read it in chapter 3.1 on page 148 of the textbook. So here are these two theorems. So the first theorem says, if we have a continuous function defined on a closed interval, a to b, so some, like 1 to 3 or something like that, and then f always attains an absolute maximum and an absolute minimum somewhere on the interval. Okay, so there's never going to be a function that just doesn't have a maximum value or doesn't have a minimum value. As long as your function is continuous and defined on a closed interval, then you will always have an absolute maximum and an absolute minimum. Okay. Oh, so this is going to be, most of the functions that we deal with are going to be continuous. So it's not going to be a very restrictive assumption. Okay, so that's the first theorem. So you can always find these. And then the other theorem, which really links this with calculus, says that if f has a local maximum or minimum it has a local maximum uh, or minimum at a point, and if f is differentiable at that point, right? So, I mean, it's possible that it just doesn't have a derivative. The limit defining the derivative just doesn't exist. That could always happen. But if it does exist, then the derivative has to be 0, right? So that's exactly what's going on this project. Oh, sorry. Some people still need the link. I guess it's not on the WhatsApp. I just sent the link. I just sent the link. Let me just resend this to the WhatsApp. Okay. Okay. So recall this theorem, right? If you have a local maximum or minimum, what's the derivative going to be? It's going to be zero, right? That's the only possibility for the derivative. So if you go over here, we've got this local minimum, local maximum, local minimum, local maximum. What's the derivative at every single point of these? Zero, 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 zero. Always a horizontal tangent line, always derivative zero. Okay? So this is exactly what we observed graphically. I'm just making it formal as a theorem. Okay. Okay.
Yeah, hello, sir.
Yes. Yes, Prince.
Yeah, I have a question with a tangent line. Can
Hmm.
a tangent line always, yeah, can a tangent line always run at a vertical?
It
Not
can
that
be.
horizontal, yeah, horizontal can it always be in horizontal form?
Well, it will be horizontal exactly at these special points, right? At the local minimum or the local maximum, it will always be horizontal. At other points, it might not be horizontal, right? I mean, we have all of these other points where I drew tangent lines also. These points are not the local minimum or the local maximum, and those songs are not those lines are not horizontal, right? So sometimes it is, sometimes it isn't. But where it is, it's telling you something very special. It's indicating that that could be a local maximum or a local minimum. Does that answer the question? I can't tell.
Thank you.
Yeah, okay.
Thank you so much.
Okay, you're welcome. Okay. Okay. So this is the most important theorem that we're going to use when we actually do applications, right? We want to know if we have a local maximum or minimum in its domain, and if the derivative exists, then the derivative has to be zero. And the warning that we have here is that this theorem doesn't work the other way around. You can have that the derivative is zero without there being a local maximum or minimum at C. So having the derivative be zero doesn't necessarily mean that you have a local maximum or minimum. But the other way around, if you have a local maximum or minimum, then the derivative is definitely zero, right? And the example of this is if we take f of x equals x cubed and we look at x equals zero. So let me draw a picture of this. Um, so if we have here, I'm going to have f of x equals x cubed. And if I draw the graph of y equals f of x, so y equals x cubed, the graph looks something like this. And if you look at let me actually redraw this. Let me redraw this. This is kind of what the graph of y equals x cubed looks like. And if you look at the tangent line at the origin, it's actually horizontal. It's actually just going to be a horizontal line. And we can figure this out, right? Because f prime of x here, we recall the power rule, right? If f of x is x cubed, f prime of x is equal to 3x squared. That's how the power rule goes, right? You bring down the 3 and it goes down by 1. So f prime of x is 3x squared, which means that f prime of 0 is 3 times 0 squared, which is 0. And so what this tells us is horizontal tangent line at x equals 0, just like what I drew here. The tangent line is actually horizontal here. But it's still not a local maximum or minimum, right? I'll use a different color here. So this point over here is not a local maximum or minimum, right? This point here is not a local maximum or minimum because look, how could it be? It can't be a local minimum because there's stuff nearby that's less than it. And it can't be a local maximum because there's stuff nearby that's greater than it. So we have that the derivative is zero, but it's still not a local minimum or maximum. It's nothing. So what we see from this example is that if you have derivative zero, you might be a local maximum or minimum, or you might not. But if you are a local maximum or minimum, then and you have a derivative, then the derivative has to be zero. That's what the theorem says. So it's a little bit subtle because the logic, it's kind of a statement and it's converse. Maybe we'll talk a little bit more next year. We'll do a little unit on mathematical logic next year. But basically, a statement and its converse are not equivalent. So here we have if the derivative is zero, if it's a local maximum or minimum, then the derivative is zero. But if the derivative is zero, that doesn't necessarily mean that it's a local maximum or minimum. Okay. So, all right. So this is just to illustrate the warning over here. And it's just illustrating this warning that we can have f prime of z being zero without there being a local maximum or minimum at c. Okay, but the theorem, which is the important thing, is if you've got one, then if the derivative exists, it has to be zero. Okay, so let's actually go as one more page of this, and then we're going to go to exercises. We'll do problems for most of the rest of the class. Okay, so what's a consequence of the theorems? So a consequence says that if you have a function f and you have a point in the domain, then we call it a critical point or a critical number for f if either the derivative is zero or the derivative does not exist. And so it follows from this other theorem that if you have a continuous function with a local extremum at c, remember an extremum means either a maximum or a minimum, if you've got this at c, then c is always a critical number for f. Okay, so the only places you can find a local maximum or a local minimum is is a place where either the derivative is zero or the derivative doesn't exist. And the other corollary of this is that if you're defined on a closed interval, and if you want to know where's the absolute maximum or the absolute minimum, well, it's either going to be at a local maximum or minimum, or maybe it's at one of the endpoints of the interval. Those are the only two things that can happen, right? So, I mean, if I have a graph like this, let's say I have a function defined on a closed interval from a to b, I could have something like this. Oh, wait, no, 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 no. Sorry. So where's the absolute minimum and the absolute maximum? Well, this point here is the absolute minimum. And here, this is going to be at a point where f prime is equal to zero, where the derivative is equal to zero. And this here is going to be, let me actually redraw this a little bit more suggestively. Let me draw it like this. Okay, something like this. This point over here is the absolute maximum. And this is just at an endpoint. Okay, so these are the two ways that you can find absolute minimum and maximums. You can find it because it's at a critical point. It's where the f prime is equal to zero, right? This is a critical point. Or you can find it at the endpoint of the interval. Okay, so this corollary is what we're actually going to use practically. It's going to say we want to maximize or minimize a function. Well, if it's defined on a closed interval and we want to find an absolute extremum, meaning the maximum or the minimum, then there's two places to look. You look at the critical numbers, so where the derivative is zero or where it doesn't exist, and you look at the endpoints. And then you just try them all and you see which is the biggest, that's the absolute minimum. And you see which is the smallest, sorry, which is the biggest, that's the absolute maximum. And then you see which is the smallest, that's the absolute minimum. Okay, so let's see how this works in an example, which I think will make it clearer, and then we can take questions after the example. So a review question, which is actually, I assigned it as a homework exercise, but I think we'll just work it like this. So find the absolute minimum and maximum of the function f of x equals x divided by x squared minus x plus 1 on the intervals 0 to 3. So what we know, let's just recall, so from the theorem, right, we need to find critical points or numbers and endpoints, right? So what are the endpoints? Well, that's easy. The endpoints are just x equals 0 and x equals 3, right? These are the endpoints of this interval. It goes from 0 to 3. So what about the critical points? What we do for this is we have to solve f prime of x equals 0. In order to get these critical points, we have to solve f prime of x equals 0. Okay, maximum 1, minimum 0. That seems plausible, but let's do this all out, right? Okay, so we have to solve f prime of x equals 0. So we have to calculate f prime of x. So now for this, we have to review that this function here is a quotient, right? We have x divided by x squared minus x plus 1, right? And so in order to do f prime of x, we have to use the quotient rule. Right? If you recall the quotient rule says that if you have g over h and you take the derivative, that's equal to h times the derivative of g minus g times the derivative of h, all divided by h squared. This is the quotient rule. It's from last term. So in order to do it for this function, what do we get? We get that f prime of x is equal to, well, we start with the denominator times the derivative of the numerator. So that's x squared minus x plus 1 times the derivative of the numerator. So that's d dx of x. Remember, this notation d dx means derivative. So times d dx of x minus the numerator times d dx of the denominator. So the derivative of x squared minus x plus 1. And all of this divided by x squared minus x plus 1 squared. So if we simplify this, the derivative of x is 1. So that's just x squared minus x plus 1 times 1 minus x times, now the derivative of x squared minus x plus 1, remember x squared becomes 2x minus the derivative of x becomes 1. And then the derivative of 1 is a constant, so that just becomes 0. So this is what we have here. And then all of this divided by x squared minus x plus 1 squared. Now, if we simplify this all, we get x squared minus x plus 1 minus 2x squared plus x. That's what happens when we multiply all of this out. All of this divided by x squared minus x plus 1 squared. And this becomes negative x squared plus 1 divided by x squared minus x plus 1 squared. Okay? And so we want to know when is this thing, we've now simplified it, when is this equal to 0? Right? We're trying to solve when this is equal to 0. We also want to know when it doesn't exist, but it turns out that the roots of this thing don't lie inside the interval from 0 to 3. So this will never be, this will always be well defined between 0 and 3. Okay. So before I move on, any questions here? Recalling this quotient rule for how we take the derivative of an expression like this, a rational function. Okay, so it is this somewhat complicated formula, but once you have the formula, you just punch everything in and you simplify it, and you end up getting this expression. So what we're really trying to solve now is we're trying to solve negative x squared plus 1 divided by x squared minus x plus 1 squared equals 0. So any questions yet about how we got here? We're trying to find these critical points where they are. Okay, great. So now solving this algebra is not so hard, right? Because we have 0 here, so we can just multiply both sides by the denominator. And so we end up with just negative x squared plus 1 equals 0, which gives us that 1 equals x squared, which gives us that x is equal to plus or minus 1, right? And in fact, we're looking at the interval from 0 to 3, so the only one that we really care about is x equals 1, right? So now we have these 3 different candidate values to try to find the maximum or the minimum, right? We got to try x equals 0 and x equals 3, and we have to try x equals 1. So now we just try them all and see which is the biggest and which is the smallest. And whichever one is the biggest is going to be the absolute maximum, and whichever one's the smallest is the absolute minimum. Okay, so let me do that on another page. I'll write this again. So we have f of x equals x divided by x squared minus x plus 1. And we're going to just go build a table, right? We have x and we have f of x. And we're going to plug in 0, we're going to plug in 1, we're going to plug in 3. So what happens when we have 0? F of x becomes 0 divided by 0 squared minus 0 plus 1. That's going to turn out to just be 0. When we have 1, we get 1 divided by 1 squared minus 1 plus 1. That's going to turn out to just be 1 divided by 1. That's going to be 1. And then at 3, we have 3 divided by 3 squared minus 3 plus 1. So that's 9 minus 3 plus 1 is 7. So this is going to become 3/7, right? So what we get is that we have the absolute maximum. We just look for the largest of the values. So the largest of these values is 1. So is 1 at x equals 1, and the absolute minimum is 0 at x equals 0. Okay. Okay, so these are the real solutions to the question. Okay, remember, what did the question ask? The question asked to find the absolute minimum and maximum of this function on a particular interval. Okay, so what do? We found the endpoints. We found the critical points. In this case, there was just one critical point in the interval because we don't care about -1 because it's not in the interval. And once we found all these points, then we punch them all into the function and we see which is the biggest. This is the maximum. And which is the smallest. This is the minimum. And that's how you solve the problem. Okay, so the biggest value you find is the maximum, and the smallest value you find is the minimum. Okay, so any questions about how we do this problem? Okay, good. Okay, so we'll do a bunch more examples. This is going to start getting, this is going to start, oh, did I get an extra? Okay, yeah, let me, yeah. So now we're going to talk about how do we apply this to word problems, right? I mean, so the problem that I just gave you some function and said to find a maximum or a minimum. It wasn't really related to anything in real life. So the question is, how do we actually apply this when we're trying to optimize some sort of quantity with some sort of practical application? So to apply what we've done to optimizing quantities in real life situations, what you need to do, you need to interpret the situation as maximizing or minimizing some function on some domain, right? This is what calculus is equipped to do, right? Calculus says if you give me a function and a domain, I can find you the maximum and I can find you the minimum. But if you have a word problem or something arising from a practical application, you probably need to do a little work to get it into a form where it can be solved by calculus. So this often requires several steps. So the first one is understand the problem. What is to be maximized or minimized? What are the constraints? Number two is if it's a geometric problem, you might want to draw a diagram, or even if it's not, you might want to introduce notation for the relevant quantities. Step three says express the quantity that you want to maximize or minimize in terms of the other quantities in the problem. This is going to give you an algebraic relation between everything that you have in your problem. Step four is use relations among the input quantities to rewrite the expression for Q so that it becomes a function of one variable. So even if you have a lot of different inputs, you may be able to rewrite things so that there's only one variable that you really need to worry about. So there's one independent variable. And once you've done step four, now you are in a position for calculus. You have a function Q that is a function of one variable on a particular domain, and you want to minimize it or maximize it. And so calculus will tell us how to do that. We check the endpoints and we look for the critical points. That will tell us, what we can get. Okay, so now we maximize or minimize the relevant function on that domain. Okay, so maybe we can go, do I want to go straight to the example? No, maybe I'll say one more thing before we go to the example. So this is our general playbook for how we do an applied problem. Any questions? All right, so no questions. Okay, so let's go and do the rest. Okay, all right. So sometimes the question that you're going to want, if the question you're trying to maximize or minimize on is a closed interval, then we already know how to do it. We check the endpoints, we check the critical numbers. Sometimes, and we'll see this in our new examples, an optimization is going to take place on an open interval rather than on a closed interval. So something like all the real numbers or all the positive numbers or the open interval from 0 to 1, not including the endpoints. And so it turns out that if you want to do an optimization on an open interval, you can use the following results. So suppose that we have a critical number for f of x. So a place where, the derivative is 0 or where the derivative doesn't exist. Well, then the first thing says that if the derivative is greater than 0 for x less than c and less than 0 for x greater than c, then f of c is the absolute maximum value of f. Let me show the picture here. The picture here is, let's say that we have our point c and we have a critical value. So if f prime of x is greater than 0 for x less than c, that means the tangent lines are going to have positive slopes. So the function will be increasing up to c. And then if f prime of x is less than or equal to 0 for x less than c, that means the tangent lines are going to have negative slopes. So it's going to start decreasing like this. So here we have f prime of x is less than or equal to 0. Here we have f prime of x is greater than or equal to 0. And what we have here, when that happens, is an absolute maximum. And then the second case is exactly the opposite, right? So here I have some c. If the derivative is negative, is less than or equal to 0 for all x less than c, so that means it's decreasing here, and then greater than or equal to 0 for all x greater than c, so increasing here, then it turns out that at c, you've got to have the absolute minimum. So this picture would look something like this, right? So here you would have f prime of x is greater than or equal to 0. Here you would have f prime of x is less than or equal to 0. And so what you're left with here is the absolute minimum. Okay, because basically it's going down, 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 down. You get to C, and then it's going up, 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 up. So when you get to C, that's the lowest that it's ever getting before it turns around. That's the nadir. So sometimes when you're on an open interval, you're not going to check the endpoints. But if you have only one critical point and you're in one of these two situations, then that's going to be good enough to just find the absolute minimum and the absolute maximum. Okay, and this is how most of our applied examples are actually going to work. So we're going to see how this works in our examples. Most of what we're going to do for the rest of the class is going to be examples that work this way. Okay, so let's actually do an example and see how this works. Okay, so this is an example that we rushed through at the end of the class a month ago. So today I want to do it slowly enough. Okay, so suppose that we have a cost function, c of x equals 16,000 plus 200x plus 4x to the 3 halves. This is the cost of producing x units of a product, say in US dollars. You can imagine this makes sense. You can imagine this 16,000 as like a fixed cost to set up your machines that you need to produce the product. Then 200 times x is a kind of per unit cost, like it's going to cost you 200 now to produce each unit. And then this x to the 3 halves term is kind of saying that if you really want to produce a lot, that's going to strain your equipment and it's going to cost, more. It's going to get, more expensive the more you produce. You're going to need to service your equipment more often or hire more employees or something like that. It's going to be a bigger per unit cost after you've set up your fixed factory if you really want to do more. You're going to be straining your resources. So this is kind of the intuition um, for a for a for a for a cost function like this. I'm getting okay, I'm just going to send a message to the WhatsApp. Okay. So what's the average? So this question has two questions. So this is our cost function. So how much product must be produced to minimize the average cost of production? And what is the average cost of production in this case? Okay. So what do we need to do going back to our checklist? Well, we've got to understand the problem. What is to be maximized or minimized? What are the constraints? So here we don't really have any constraints. And what we want to do is we want to minimize the average cost of production. So there's not going to be a diagram, right? We don't need a diagram for a question like this. It's not geometric. And we already have the notation, right? X is the number of units that you're going to produce. And so what we want to do is express the quantity Q. This is going to be the average cost. And we want to express it in terms of the other quantities in the problem. So that's what we're going to do here for question 3. So we're going to say here is Q. So average cost means cost per unit. Okay. So we'll have here that, sorry. Q is equal to the average cost per unit. And this is equal to 16,000 plus 200x plus 4x to the 3 halves. That's the total cost divided by x, which is the number of units, right? Total cost and the number of units. Oh, wait. Oh, God. Oh, did I do a wrong? Oh, God. Oh, no, I made a typo. Okay, so I'm sure this is right, James. It's probably right, as you were right the last time. So let's go through this first. So let's simplify this, right? So we can write this as 16,000 divided by x plus 200 plus 4 times x to the 1 half, right? Because we have x to the 3 halves divided by x, that's x to the 1 half, and here we have 16,000 over x. All right, so James, how did you come to your answer? So what do we have to do now that we have this equation for the average cost per unit? Okay. Well, even without video, yeah, okay. So yeah, you can type if you need to. Um, okay. Well, okay. I'll do this. So what we have to do here, right? This is the average cost per unit. So we can call this f of x. And so now we take the derivative and set it equal to 0. Again, we want to find the critical numbers, which means we have to solve f prime of x equals 0. So what do we get for f prime of x equals 0? Remember here, if f of x is, I'm going to write this as 16,000 times x to the minus 1 plus 200 plus 4x to the 1 half. That means f prime of x here, we can just use the power rule. So that's going to be negative 16,000 times x to the negative 2, right? The minus 1 goes down and gives us a minus 2. Then 200 is a constant, so this just disappears. And then 4x to the 1 half becomes plus 1 half times 4 times x to the negative 1 half. Or in other words, negative 16,000 x to the negative 2 plus 2x to the negative 1 half. Okay, and we want to solve this being 0. Okay, so doing this algebraically, this gives us that 2x to the negative 1 half equals 16,000 x to the negative 2. Okay. And if we want, we can multiply both sides by x to the negative 2, or sorry, multiply both sides by x squared, and that'll give us that 2 times x to the 3 halves equals 16,000. Right, I'm multiplying both sides by x squared. And then I can divide both sides by 2. This will give me that x to the 3 halves equals 8,000. And if I want, basically an easy way to do this is I could take the cube root of both sides, right? So I could take a cube root of both sides now. The cube root of x to the 3 halves is x to the 1 half, and the cube root of 8,000 is 20. So this gives us x to the 1 half equals 20, and then squaring both sides, this gives us that x is equal to 400. Okay, so this is a kind of exponential equation that we have to solve with algebra. But when you solve it, you get that x is equal to 400 over here. Okay. So we're not done with the problem yet, but we solved this equation. So the critical number, there's only one solution, and it's going to be that x is equal to 400. Are there any questions about how we got to x equals 400? Okay. So 400 units, right? Remember, x represents the number of units, right? X, we already have that here. X is the number of units. Okay, so x is equal to 400 here. That's the number of units. So now we just want to check what happens, well, when this is our derivative. So maybe I'm not going to check this right now, but you can check that when x is less than 400, that this tells us that f prime of x is greater than or equal to 0. And when x is greater than 400, f prime of x is less than 0. You have to check that just by using the formula. But maybe I'll skip that for now. Right, so that's 20 squared. So maybe I'll skip that for now. And so that means we're in the situation of the theorem, right? So sorry, other way around. Other way around. So when x is less than 400, f prime of x is less than or equal to 0. And when x is greater than 400, f prime of x is greater than or equal to 0. So this tells us that you get the minimum average cost at x equals 400. You get the minimum average cost at x equals 400. Okay. And now, as James said, what is the average cost of production in that case? Well, then we just have to plug in 400 to this function, right? Just as James said. And I assume we're going to get 320. Let me use another page just to see what we're going to get. So the minimum average cost, well, we're going to plug in x equals 400 to this f of x, which we had was 16,000 over x plus 200 plus 4x to the 1/2. And so f of 400 equals 16,000 over 400 plus 200, and then plus 4 times 400 to the 1/2. Right, that's the what we get. And the average cost of production is, so what is this? This is going to be 16,000 divided by 400 is 160 over 4, so that's 40 plus 200, and then plus 4 times 400 to the 1/2 is 20. That's the square root of 400, and that's exactly right. Perfect. Thank you, James. So we get exactly 320, which is exactly right. Okay, so 320, and this is maybe US dollars per unit, producing, I don't know, TVs or something like that. Okay. So, there were some computations that we had to do, but basically how you do this problem is just you've set the derivative equal to 0. You're finding, in this case, the one value where it's equal to 0, which is x equals 400. That's going to minimize the average cost of production. And then once you have that value, you plug it in, and that will get you the average cost of production. Okay, so this will give you $320 per unit. And that's what you get when you produce 400 units. Okay. All right. Any questions on this problem? Okay. All right, no questions. We're basically just going to do more examples for the rest of today. So example 3. Find two positive numbers whose product is 100 and whose sum is minimal. Okay? So if we go back to our roadmap, what does our roadmap say? We've got to understand the problem. What is to be maximized and minimized, and what are the constraints? And we may want to introduce notation for the relevant quantities. Again, a diagram's probably not going to be so helpful here, but we'll want to introduce some notation for the relevant quantities. Okay? So here what we may have is, so the two positive numbers, maybe we'll say we'll let, x and y be the two numbers. Okay? And what we want to do is we want to minimize, what's the quantity that we're trying to minimize? Well, it says we want the sum to be minimum. So we want to minimize the sum of the two numbers. We want to minimize x plus y. And what's our constraint? The constraint is that their product needs to be 100. So you have to have xy equals 100. Okay. And maybe also that x and y both have to be positive. So we want to minimize this sum, but our constraint is that xy equals 100. Okay, so this is basically where we're setting up the notation that we need. So I want to see how many more do we have? Oh god, we have a lot of examples. Okay, we may not get through all of the examples. That's fine. Okay, so the constraint is that xy is equal to 100. So now if we go back to our general strategy, it says, so Q is this x plus y. This is what we're trying to minimize. Okay. So now it says use relations among the input quantities to rewrite the expression for Q so that it's a function of only one variable on a particular domain, right? We don't know how to maximize or minimize things with two variables. In general, you can do this, but it uses multivariable calculus. It's not what we're doing right now. We're trying to make sure that everything can be expressed in terms of one variable. But we start with x and y, which are two variables. So we need to somehow change things so that it's only in terms of x, that we don't have any y's anymore. That's what this step 4 is over here. Okay. Well, what do we have? We know that x times y is equal to 100. So we need to get everything in terms of x. Well, luckily, our constraint tells us that we can use, instead of xy equals 100, we can write y as 100 divided by x. Right? Y is equal to 100 divided by x. And that means every time we see a y, we can always just rewrite it as 100 over x. So this is because we know that xy is equal to 100. Okay? So what happens here, so now we are minimizing our quantity q, which is f of x, which instead of writing as x plus y, instead I'm going to write it as x plus 100 divided by x, right? Because this thing is really y. It's 100 divided by x because of our constraint. And what's our interval? Well, we just need that x has to be a positive number, x has to lie somewhere between 0 and infinity. It's got to be a positive number. So James is certainly right. The two positive numbers are 10 and 10. Let's see how this comes out. Okay? So now we've gotten it into the situation where we're actually doing calculus. We have a function of one variable, x plus 100 over x, that we're going to minimize over a particular interval. So now we find the critical numbers. And what do we get? We get that f prime of x, well, the derivative of x is just 1, And I guess the derivative 100 over x, another way that you could write this is 100 times x to the minus 1. And we know we can use the power rule to evaluate that. So what f prime of x is going to be 1 plus negative 1 times 100 times x to the minus 2. And we want to set that equal to 0. So this tells us that 1 minus 100 x to the minus 2 equals 0, which gives us that 1 is equal to 100 x to the minus 2. Multiply both sides by x squared. This gives us that x squared is equal to 100. And then this gives us that x is equal to 10. Notice they have to be positive numbers, so we don't take minus 10. It's only going to be positive 10. Right, so this gives us that x is equal to 10. And then, well, the two numbers have to have product 100. So if x is equal to 10, then y also has to be equal to 10. So y is 10 as well. Okay, and their sum is 20. And so it turns out that, this is your answer, right? So x and y are both going to be 10. Okay, that's the smallest. Though if I take two numbers whose product is 100, 10 and 10 is the way that they have the smallest sum, right? They could have, they think about some other things, right? Well, 5 times 20, their sum is 25. 2 times 50, their sum is 52. 1 times 100, their sum is 101. The best you can do is 10 times 10, but what this does is it actually proves it. It says you can do it as 10 times 10 because you can set this up as some quantity that you're trying to minimize. And using calculus, you can show that the only place this can have a minimum is going to be at the critical point. Okay? And maybe you can check also if you want that whenever x is greater than 10, that this quantity is going to be positive. And whenever x is less than 10, this quantity is going to be negative. So it's again going to be a minimum. So in this case, we have x equals y. Right? So it's the only choice. All right. Any questions here?
Well, I think everything is clear, Doc.
Everything's
You
clear?
can
Okay, good.
continue.
Okay, good. Okay, so let's go to another example. Okay, so this was a homework exercise. It's number 3. I actually want to do it before number 2. So Joseph makes and sells necklaces at the beach. Last summer, the necklaces cost 150 Liberian dollars each, and 20 were sold each day on average. When he increased the price by 10 Liberian dollars, he found that the average decreased by 2 sales per day. So assuming a linear relation between price and quantity, what is the function f of x given the number of necklaces sold as a function of price? And what should Joseph set the price of a necklace at to maximize his total revenue? Okay, so we have two questions here. So first of all, what is this function? This is not a calculus question. It's just asking us the function. And then this over here is the calculus question. It's what should the price be of a necklace in order to maximize what? To maximize the total revenue. Okay? So we have to answer the first question in order to solve the second question. So for the first question, okay, we know that, 150 Liberian dollars means 20 sales, and 160 Liberian dollars means 2 fewer sales, so 18 sales. Okay, so let's make a key, right? So if we let, I don't know, if we let x equal the price, and y equals the number of sales. Well, how can we want to write y as a function of x. So write y as a linear function of x. Is we're going to write y as a linear function of x. So what do we have to do here? We have to see, this is, remember, going back to functions, to write a linear function, we have to know what's the slope, right? So the slope is what? Well, when we increase by 10 Liberian dollars, we decrease the sales by 2. So in this sense, the rise is going to be -2 because the sales decrease, and the run is how much you increase the input. That's divided by 10, or so that's -0.2. Okay, so that's going to be the slope. And so then probably the easiest way to do it is to write, is to just do point slope form. So to do point slope form here, we know we have a point where x is equal to 150 and y is equal to 20. So in point slope form, we can write, y minus 20 equals, well, this -0.2 is the same as -1/5, equals -1/5 x minus 150. And so if we want to really rewrite this, we could write this as y equals 20 minus 1/5 x plus 30, or y equals, that's going to be the same thing as 50 minus 1/5 x. Okay, so this is the answer to the first question. Okay, the number of necklaces that's being sold is going to be 50 minus 1/5 of the price. Okay. And of course, this doesn't make sense in full generality because, what you get, eventually you get dealing with negative prices or negative quantities, which don't make any sense. But at least in a range close to the original data, it's reasonable to assume this kind of linear relation between price and sales, as long as you're not varying the price too much. In any case, the problem tells you to do that. Okay. So this is the first question. So what is the function f of x giving the number of necklaces sold as a function of price? This is what it is. So if we want to use the notation of the question, it's f of x equals 50 minus 1/5 x. Okay, you have to figure out the slope using rise over run, right? That the slope really is 18 minus 20 divided by 160 minus 150. Okay, that's what this -0.2 comes from. And this here, this 18 minus 20, you can think of it as delta y, and this 160 minus 150 is delta x. Change in y and change in x. Okay, any questions about how we got this? Yeah. Okay, so James has a solution to maximize the revenue, which I'm certain is correct. So let's see what we do. So now we're doing a calculus question. So what should Joseph set the price of a necklace at to maximize his total revenue? So again, we'll use another page. These maximization questions tend to take a little while to solve. So we have that, f of x equals quantity sold equals 150 minus 1/5 x. So what's the total revenue? Total revenue is your price times your quantity, which is equal to, well, x is the price, and the quantity sold is 150 minus 1/5 x, right? That's the total revenue, 150 minus 1/5 x. And if we want to simplify that, that's 150x minus 1/5 x squared. And this is what we want to maximize, right? And so we basically want to maximize this for x well, what's the amount of necklaces you can sell? Well, any number, right? So between, or what's the price? X is the price, right? So you could set the price at 0, or you could set it all the way up to infinity, right? Okay. So now we don't have any constraints. We don't have any extra variables. We don't have any diagrams. So we can go straight to just setting the derivative equal to 0 and seeing what we get. So now we're doing calculus. So we set f prime of x equals 0. Oh, well, maybe I don't want f of x. So maybe I'll call it a new function. So we'll let g of x be this function, 150x minus 1/5 x squared equals the revenue function, where x
What
again.
do I do?
Yes, question?
Yeah,
William.
man.
Mhm. Hmm. Okay. So let this be 150x minus 1/5 x squared, right? So now we just set g prime of x equals 0 like we usually do. So the derivative of 150x is just 150. And then the derivative of 1/5 x squared is 2 times 1/5 times x. Set this equal to 0. So this gives us that 150 is equal to 2/5, sorry, 150 is equal to 2/5 x. And that gives us that, right? I think this is right. 150x minus 2/5 x. And that gives us that, this seems not quite right. Did I do something wrong here? It seems like we're setting the price at something way too high. No, I guess it's right. Okay, so, and this is going to give us that 750 is equal to 2x, and that's going to give us that 375 is equal to x. Okay, so it turns out that that actually is what's going to maximize the revenue. So Joseph is selling his necklaces way too cheaply. They're really, really nice necklaces, and he should be making them more expensive in order to maximize his revenue. This seems, I'm a little, sorry, I copied this down wrong. I knew something was wrong here. Forget it. This is all wrong. Sorry, sorry, sorry. I just copied it down wrong. It's not 150 minus 1/5 x. It's 50 minus 1/5 x. Sorry. I copied the problem wrong from one page to the next page. So that's 50, and this is 50 x minus 5x squared, and so this is 50x. Okay. 50x minus 1/5 x squared. Okay. And so g prime of x now is going to be 50 minus 2 times 1/5 times x. So we're going to set 50 minus 2 times 1/5 times x equal to 0, which is 50 equals 2/5 x. And this ends up being solved by x equals 5/2 times 50, which is equal to 125, exactly as James said. I knew I was wrong because I didn't get the same answer as James. Okay, so 125. That's exactly right. So this is the revenue maximizing price. Okay. All right, so once we have the equation for what's the quantity sold, then we can write down a function for the revenue, and again, maximize this, in this case, using calculus. Okay, and again, maybe we should observe that if x is less than 125, this is going to give us that g prime of x is greater than 0. And if x is greater than 125, that g prime of x is less than 0. And that means that we're going to have a maximum, right? That means that at 125, the derivative is greater and then it gets less. That means this thing is going to be a maximum, like for the theorem. Apologies if this writing is a little too small. Okay. So the revenue maximizing price is 125 Liberian dollars. Any questions on this example? Okay. No questions. Okay, then we have time, I think, for one more. I think I don't want to do this one. This one's going to be a little complicated. I want to do a different one. So this one maybe we'll do next time. This one is a little tricky, but I encourage you to think about it. It was a homework exercise for this time. Can put it again, but maybe I'll just draw the picture for this. So a fence 8 feet tall runs parallel to a tall building at a distance 4 feet from the building. What is the length of the shortest ladder that will reach from the ground over the fence to the wall of the building? So your diagram here is, here's your building. Here's your fence. This is your fence. And the fence is 8 feet tall, and it's 4 feet away from the building. And now you have a ladder that you want to reach over the fence and reach the building from some point on the ground. So this is your ladder. Okay. And the question is, what is the shortest ladder that will reach from the ground over the fence to the wall of the building? So this is a fairly challenging question. Maybe I won't say anything more about it. You can assume, I mean, everything here is a right angle. These buildings are straight up. So this is going to require a little bit of geometry, a little bit of similar triangles, and also some calculus to figure this out. But my hint on this, I want to skip it and I want to do a different example. Hint is let x be as in the diagram. So x here is going to be this quantity right here, this distance from the ground to the top of the ladder. Okay, and then the question is, given x, can you get a length of what the length of the ladder is going to be? You're going to have to use some similar triangles and the Pythagorean theorem. And if you can do that, then you get the length of the ladder as a function of x, and you can minimize that using calculus, and you'll get the shortest possible ladder that will work. Okay? But maybe I won't say anything more about this now. We'll deal with this next week. For now, we'll just leave this the way it is. Okay. All right, but I'll leave this example because what I really want to do to finish up class is to do this example over here. Oh yeah, so find the point on the line y equals 2x plus 3 that is closest to the origin. Okay, well, that was fast. That was very, very fast, James. So maybe right. I'm kind of impressed how fast that is. I certainly couldn't solve the problem that quickly, but seems plausible. 16.97 feet looks about right. So, we'll see. We'll see what it is. Okay. So, okay, example 4. Find the point on the line y equals 2x plus 3 that is closest to the origin. Okay, so here we may want to draw a diagram. Okay, so we have the line y equals 2x plus 3. What does this line look like? Well, here it's certainly going to go past through the point 0, comma 3. And then it has a slope of 2. Okay. So you have, I see, James. So you did that as part of your assignment. All right. Well, I'm sure it's correct. At some point when you get your data reimbursement, you can send it to me. Okay. So this line is y equals 2x plus 3. Okay. And we want to know what's the point that's closest to the origin. It looks like it's probably going to be some point over here. Okay. So what do we have? We want to so closest to the origin. This is telling us that we want to minimize a distance, right? Minimize distance from a point on the line a point x comma y on the line to the origin. Okay, let's minimize the distance from a point xy on the line to the origin. Great. Well, so what is that distance? Well, we know that we have the distance formula. If we're looking at the distance between some point x comma y and the origin 0, 0, well, then the distance is equal to, we have that d squared is equal to x minus 0 squared plus y minus 0 squared. Or d is equal to square root of x squared plus y squared. Right? Because we're looking from x to 0 and from y to 0. Okay. 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 So what do we want to do? Now the problem is we can't deal with two variables, right? So our constraint, we have a constraint here, which is that we're not just looking at all points x, y, it's got to be a point on this line. So our constraint is exactly given by the equation of the line, right? The constraint is y equals 2x plus 3. Okay. So y equals 2x plus 3 is the constraint. And so that means if we want to get everything in terms of one variable, if we want to get everything in terms of one variable, we have to use that y equals x 2x plus 3. So in this case, d is going to be the square root of x squared plus, well, instead of y squared, we're going to have 2x plus 3 squared, right? I'll be right back in 1 minute. I just have to answer my door. Okay, sorry about that. Okay, so let's finish this up. So we want to do this. So, and if we want to write this out, we can write this as the square root of x squared plus, well, 2x plus 3 squared. We have the 2x squared plus 2 times 2x times 3, and then plus 3 squared, right? That's how we do this, expand out this square. And if we simplify that, that becomes x squared plus 4x squared plus 12x plus 9. And if we simplify that further, that becomes 5x squared plus 12x plus 9. Okay, so this is the quantity that we're trying to minimize, right? This is the quantity that we're trying to minimize. Okay. Now, we could just try to minimize this by taking the derivative, but the problem is that this derivative requires something called the chain rule, which we haven't learned yet. We will learn it in a couple of weeks, but we haven't done the chain rule yet. So what can we do instead? Well, one thing to realize is that if you're trying to find the x that's going to minimize this square root, that's going to be the same x that will minimize the quantity under the square root, right? If you want to make this whole thing the smallest, that's the same as just trying to make 5x squared plus 12x plus 9 the smallest, right? Because whatever gives you the smallest quantity under the square root will also give you the smallest quantity after the square root. So this is a key observation. So let's observe, observe the x that minimizes 5x squared plus 12x plus 9 also minimizes square root of 5x squared plus 12x plus 9. But the former is easier to work with. Okay? So let's, instead of worrying about taking a derivative with the square root, which is going to get kind of complicated, let's just take the derivative of 5x squared plus 12x plus 9 and minimize that. Okay. So that's all that we have to do. So minimize, let's call it f of x, equals 5x squared plus 12x plus 9. And this is for, yeah, I multiplied all the monomials out, right? This is what we have over here. So we had x squared plus 2x plus 3 squared. So this is x squared plus 2x squared plus 2 times 2x plus 3 plus 3 squared. So that's x squared plus 4x squared plus 12x plus 9. And it simplifies to 5x squared plus 12x plus 9. Okay. Okay. Let me add this here that this is y over here. Okay. So we're going to minimize this now. So this is pretty easy. We just set f prime equal to 0. So f prime of x here is going to be 2 times 5 times x. You bring down the 2. And then plus 12. That's it. So this is equal to 10x plus 12. And we want to say 10x plus 12, and we want to set this equal to 0. That's going to give us that x, or 10x is equal to minus 12, or x is equal to minus 12 over 10, which is equal to negative 6 over 5. Okay, so this is our answer for x, which looks about right. I mean, right, this point over here is probably the closest. It's the one that makes a right angle, and that looks like it's about negative 1.2, negative 6/5. And so what is the distance? So then the distance, so I mean, we've answered the question. So find the point on the line that is closest to the origin. Well, we have x equals negative 6/5. What's y? Well, the equation was y equals 2x plus 3. So that's equal to 2 times negative 6/5 plus 3. And that turns out to be equal to 3/5. It's negative 12/5 plus 15/5. That's going to be 3/5. So what you get is that the point x comma y is the point negative 6/5 and then 3/5. Okay, or if you want to write it in terms of decimals, negative 1.2 and 0.6. Okay, yeah, so this is right, it's quadratic form exactly. So this is the point that's going to be closest to the origin. So if we label it back on this diagram, this is going to be exactly the point negative 1.2 and 0.6. Okay, any questions on this? Great. You're welcome. Okay, so the thing about these optimization problems is they're all a little bit different from each other, right? Each problem has its own kind of setup. You don't know whether you're going to have an open interval or a closed interval. You don't know whether everything will be in terms of one variable to begin with, or if there's going to be two variables and you're going to need to use the constraint to get it all in terms of one variable. Okay, and then even in individual problems, there's going to be interesting things like, well, this is the quantity you want to minimize, but actually it's better if you just forget the square root. You'll get the same result, right? So these optimization problems, because they can be applied to so many different situations, it means that they work very differently from each other. And the only way to get good at them is to do a reasonable amount of them to practice. So sometimes they involve geometry. This involves a little bit of geometry. This one involves even more geometry, so maybe James will present a solution to this one next time. But this one involves some similar triangles to try to figure out the size of the ladder. And so they're all very different from each other. So you just have to do a bunch of them to get comfortable with them. So there's three more kind of good practice questions for this week. So the first one, very straightforward, just find the critical numbers of the function t to the fourth plus t cubed plus t squared plus 1. And that's just finding critical numbers, so that's not so bad. Number two, if a and b are positive numbers, find the maximum value of f of x equals x to the a times 1 minus x to the b on the interval 0, 1. So this is still just kind of a math question where you have to find the critical points and the endpoints and see what's going to be the maximum. So you'll have to use the general power rule and the product rule for this. So it'll serve as good practice of the power rule and the product rule. And then number three, a little bit more of an applied problem. So a rectangular storage container with an open top is supposed to have a volume of 10 cubic meters. So the length of its base is twice its width. Material for the base costs $10 per square meter, and material for the sides costs $6 per square meter. And we want to find the cost of the materials to make the container as cheap as possible. Okay, and the hint is to try to express the cost of materials completely in terms of the width of the container. So I'm not going to tell you too much about how to do this, but let me just draw a picture at least. Right, this is your container, this is your box, and this is going to be your length, and this is going to be your width. And you know that the total volume is equal to 10 cubic meters. Right. So the question is, and the top is open, right? This is open. That means no top. All right. And so the question is, how can you build this? What are going to be the dimensions to build the cheapest box, and what are the materials going to cost for those dimensions? So you're going to need to be using, right, the bottom of the box and all four sides of the box. You're going to need to build them all. Okay, so maybe I won't say anything more. We can talk about this a little bit more next time, but it'll require, again, a little bit of geometry and a little bit of substitution in order to make sure that when you actually do the calculus, you've gotten everything in terms of one variable. And my hint is to make that variable the width of the container. So I would say set x to be the width of the container and see if you can write an expression for the cost of all the materials as a function just of x. Okay. All right. So that's the homework exercises. And as always, thank you for your attention. Please type your name in the chat if you haven't already done so. And next week on January 30th, we'll probably spend the first half on optimization just because I want to go over all of the questions carefully. And then we'll talk a little bit more about how we can use calculus to draw and analyze graphs of functions. Okay, and if you want to look over this in the book beforehand, this is chapter 3.2. Okay. So actually, let me make sure that's right. This is chapter 3.2. No, sorry, this is chapter 3.3. 3.3, and maybe a little bit of 3.4. Okay. All right. So thank you, as always, for your attention. Please type your name if you haven't done it so far. And please let me know if you have any questions. And also, well, I guess no, Sange's. Oh yeah, yeah. If Sange, if you're on there with Alexander, I don't know if you want to say anything about how the data distribution will work. Okay. All right. If there's no other questions, then thank you very much. Have a good weekend, and I'll see you all next Thursday. Make sure everybody typed in their name. Um, Francis did this. William, yes. Everybody did their name. Just double checking that everyone's done their name. Yes, I think we did. Okay, everybody's good. All right. Thank you all again, and I'll see you next week.